I guess we can get started now. So please do continue. Sorry for the technical difficulties. Let's get started.
Yeah, no worries at all. Sounds good. Hi everybody. My name is Megan Gran. So a bit on my background. So when I was 11 years old, I started working with Lego Mindstorm Robotics. I never actually competed. I just did it for fun, just through my school, and then it inspired me in 2012 and 2017 to actually compete in the Canada-wide Science Fair. On the upper left here, you can actually see one of the robots that I built. And then I medaled bronze both times. And then throughout high school, in between 2012 and 2017, I also did FIRST Robotics, as you can see here. I was the captain, electrical lead, Dean's List nominee, and I was also part of the drive team. Not all of those at the same time, but all of those at some point in my 4 years in high school. And now on to today, or more recently. So when I was in my second year of university, I applied to this opportunity called the Fly a Rocket program with the European Space Agency. So the European Space Agency every year runs a number of training programs, educational programs, and this one really caught my eye and was super exciting, the Fly a Rocket program. So I actually was one of the 24 students to be selected, and I got to go to Norway, and I spent about 2 weeks with a team of students from all over Europe, and we built a rocket together, and then at the end of the week, we actually got to launch it. So that is our rocket down in the right corner here. This is me with a model of the rocket. It's not the exact rocket that we launched, but it is the same shell that we launched, and it was super cool. And so just a list of things that I've done since then or that I do now. So now I'm in my fourth year at York University, the Lassonde School of Engineering. I'm also a full-time co-op student at KPM Power in Etobicoke. I build and design electrical systems. And also part-time, I am a dark matter research student with the University of Goethe in Frankfurt, Germany, and it's also a partnership with York University. So I do that as well. I also have ADHD, ADD, depression, and anxiety. I think that's important to mention with you guys being such a young age group because you guys might have these diagnoses, you might get them in the future, and just know that, you can continue to do great things aside from anything that might be aside from ADHD and all that. As well, I have two cats that I recently adopted in the pandemic. This one here is Pepper, and then this is Trixie, my tripod. She's missing her back leg, but she doesn't know that she's missing it, so no one tell her. Okay, so what is space engineering? What's a space engineering student going to do if I'm not going to talk about rocket science? So I want to give you guys a brief introduction to rocketry and orbital mechanics. So yes, this is literally rocket science. You guys are literally learning about rocket science today. So first of all, what's a rocket? It is a cylindrical projectile that can be propelled to a great height or distance by the combustion of its contents, used typically as a firework or a signal. So, yep, that's pretty much anything that explodes and flies some kind of distance. It can be called a rocket if it's a cylindrical shape. So, the major equation behind rocket science, why everything with rockets work, the way that they can get up into space, uh, is Newton's second law, which is this equation that's in front of us. And you guys, most of you guys are in grade 10 or younger, so you might not have seen this equation yet, but if you take sciences in grade 11 and 12, specifically physics, you're going to be seeing this equation a lot. You also might see it in math as well, but this is Newton's second law. So this on the left here is force, and on the right we have mass times acceleration. Now, what does that even mean? The mass is generally the weight in kilograms of an object. So not necessarily weight because weight and mass are different, but the weight in kilograms of the object. And then acceleration would be the rate of change of the speed. So yeah. So now looking at the rocket equation. So these rocket equations are what they actually use to calculate the different pieces of information that you need to be able to launch a rocket up into the air or up into space, depending on where you want to go. Because sometimes you don't want a rocket to go all the way into space. For example, the rocket that I launched, it was just a science rocket, and so it went about 8 kilometers in the air, and it went over 300 kilometers in distance, I believe. But we recorded all kinds of data on the weather, the temperature, the humidity, the location of the rocket, and how the temperature of the rocket changed from the nozzle to the back of the rocket, so from the front to the back of the rocket. And then we were able to graph all that information. We also actually worked on the rotation of the rocket. But yes, these are the equations that are used in all different kinds of rocketry programs that you would use to actually map out rockets. So this funny little symbol here, this is delta, which just means the change in. So here we're talking about the change in velocity. And these, so yeah, exactly. It says it here, the change in velocity, the exhaust velocity, so the velocity leaving the rocket, the initial launch mass, so how heavy the rocket is, and the final dry mass, which means basically this is talking about the difference in the fuel. So you have the rocket full of fuel, and then, it's basically saying how much fuel there is. That's why they're one over the other. And then, yeah, there's all different ways that this equation is typically used. Um, there's all different forms of this equation, but these are the basics of how they actually calculate what you need to put a rocket into space. And so this is a model of a rocket. This, I believe, was actually from my European Space Agency notes from some of the projects that we did a number of assignments leading up to the actual launch to continue to qualify for the program. So this little arrow here with the D, this represents drag. So this is one of the forces, um, like we talked about the F equals ma. This is one of the forces that we have to consider because this will change the direction of our rocket, how high it goes, how far it goes, how fast it goes. It is one of the most important pieces of information when it comes to rocket science. And as well here we have mg, which is short for mass times gravity. So there is a gravitational acceleration that we experience on Earth. It's the reason, why you can stand up straight, the reason why when you jump, you don't fly off to Mars. And it's even, it's responsible for a lot of things on Earth. And the number for that on Earth is 9.8 meters per second squared. That's just the typical number that we use to calculate it. And then the mass you would multiply by the mass of the rocket. So how heavy your rocket is. And then that will give you the bare minimum number that the rocket can actually be able to lift off of the ground. And so, yeah, and then we have here the velocity. These funny looking symbols are just symbols representing the different ways that you can point the rocket. Um, but the main points here are drag and the mass times the gravity. And those together are how you calculate the force, which is what you will need to know in order to how much force and how much thrust you'll need to push the rocket off the ground and get it to where you need it to go. So now how does this relate to orbits and orbital mechanics? So an orbit is a curved path of a celestial object or spacecraft around a star, planet, moon, especially a periodic elliptical revolution. So now what the heck does that mean? That was a lot of scary words. So a celestial object is basically anything outside of Earth's atmosphere. So in space engineering, we typically consider the end of Earth's atmosphere 100 kilometers above the surface. And it's not a hard set line because there is no kind of like, we're not necessarily in a bubble, um, if that makes sense. So there's no specific point to which Earth actually ends or the atmosphere actually ends, but it's always approximately around 100 kilometers above Earth's surface. So when they say a celestial object or a spacecraft, that's anything above 100 kilometers above Earth, and a periodic elliptical revolution. So, if you guys have ever seen an elliptical specifically at the gym, the thing that you put your feet on and that you're moving like this, the reason why it's called an elliptical is because the motion that your legs are moving in is an elliptical motion. So, an elliptical is just basically a way of saying an oval, except it's referencing movement. So it's kind of like saying moving in an oval. And periodic just means that it has some kind of pattern or rhythm to it, and revolution just means around. So a curved path of an object that is outside of Earth, especially if it has some kind of uh, rhythm or path and it is in an elliptical motion. Another thing to note, circles are ellipticals, but ellipticals are not circles in the same way that squares are rectangles, but rectangles are not squares, if that makes sense. So yes, orbital mechanics is essentially the understanding of the movement and elements and components in the orbits. So how do they relate and how are they different? I'm just going to check my time here. So another important part, there's a couple names when you're talking about space science and space engineering that will come up a lot. So Newton is one of them. Newton was this equation back here. This is Newton's second law. And then another one is Kepler's law. So Kepler's law are laws relating to orbits. And a lot of the times in space engineering, a lot of the things that I do in class is using Kepler's laws and Newton's laws together to look at different orbits and things. So with Newton's laws, we can look at the gravitational pull of everything, the effect of everything. And then with Kepler's laws, we can actually begin to look at it from an orbital perspective outside of Earth. Because in space, you're not going to be feeling the same effects of gravity. So once you pass that 100 kilometers, that von Karman line, once you're out of the Earth's atmosphere, then you still have Newton's second law apply. It's just now the acceleration, it's not going to be necessarily the pull of the Earth. There's going to be much more things to consider and different things to consider, which is why then we use Kepler's laws here. So, Kepler's laws. So, like I said before, the elliptical is just in reference to a motion in an elliptical or an oval shape. So these are all the different parameters, all the different things we consider when we're looking at something going around the sun, going around the earth. In this image, it just shows the sun. So for example, this would be us around the sun. I think our orbit is much more circular than that because we don't go that far out. But I think this is just from a satellite that goes around the sun. So if you look on the left here, this is something that's really interesting. So one of the important things of that we found, I think it was through Kepler's laws, or there is another law that you can actually use to solve different orbital parameters, so all these numbers here on the screen, is that this red area here is the same size in surface area, so like kilometers square, as the green area here. So then we know, like it says down here, the satellite must use the same time from T1 to T2 as it does from T3 to T4. So I don't know if that makes a lot of sense because it's a little weird. It's a hard concept to think about, but yes, this amount of time took the same as this amount of time. So think of a um, a figure skater spinning in a circle. You know when they spin super, super fast? What do they do when they spin super fast? They pull their legs and their body in really tight, and then they're able to spin. That's because the closer all of their mass is to their center of gravity, the faster they will go around on the outside. And that's exactly what happens here. So even though this goes so much farther of a distance, it's so much closer to the body, the center of mass that it's orbiting around, that it moves so much faster than it does out here. So this, in the same amount of time, it was only able to go this far, but that's because it's far out from gravity. So then think if a figure skater were to stretch their arms out, they wouldn't be spinning as fast.
So I have
Okay.
a question then. So
Yes.
let's say T3 and T4 were closer. So instead of being on the opposite side, so if this is the sun, instead of being on this side, what if they were like, maybe like over here, whereas T2 and T1 were over here? You get what I mean?
Uh, so like if I can't see your screen right now, so are you saying if T3 and T4 were up here?
Yeah, if T3 and T4 were somewhere in that region, would that law still apply? Because they're not
Of
necessarily
course.
as closer to the sun.
Yeah, it would absolutely still apply. It just wouldn't be in the exact same um, like the exact same distance that it would cover. So for example, for T3 and T4, if they were moved to up here, the distance that it would travel would kind of be somewhere in between these two sizes. So since this is the farthest point away, that's kind of like the slowest or the least amount of distance it can take in that amount of time. And then this T3 and T4 is like the farthest amount of distance it can take in that amount of time. So if you're doing it up here, you would just kind of take like in between the two. So then it would just be like a halfway point between the two. So for example, if you say this is 1 unit in distance and then this is 2 units in distance, then to go somewhere here, the distance that it would travel would be 1 plus 2 divided by 2, which is 1.5. So then it would like essentially be somewhere in between the amount of distance, but that law absolutely still applies.
Yeah, thank you for that.
No problem. Are there any more questions? Feel free to interrupt me at any point with questions.
I was just wondering when would this be used in like real life scenarios?
So these equations are used when we're talking about satellites. So this could mean natural satellites. So basically, the definition of a satellite is anything orbiting around another body in the universe. So the moon is actually what they call a natural satellite for us because the moon is orbiting us. So it's called a natural satellite. So we use these equations to predict all different kinds of stuff about the moon, its location, where it's going to be. So, for example, I think that's how we can find out when all these different eclipses are going to be, because we can actually find like where in this curve, like if this is us, if this is Earth, not the sun, we can find out where exactly the moon is going to be in this curve, and then where exactly we are going to be on the sun's curve, and then we can find out things, yeah, like eclipses. And that's just one example. These equations are used for any kind of satellite. Um, so if you know any of the Canadian Space Agency satellites or the European Space Agency satellites, so like RadarSat, they have to use these equations to be able to know how much fuel they're going to be bringing on their satellites, because they're going to have to be adjusting their orbit to make sure they fly over the parts of the Earth that they want to fly over. They use these for um, the International Space Station is a huge example. The International Space Station has a very specific orbit, and it stays very, very, very close to that 100-kilometer von Karman line. I think the International Space Station is actually only 150 kilometers above Earth's surface. And when you get to that 100-kilometer line, it will actually begin to fall back into Earth. And so, since it's so close to it, the International Space Station has fuel on it to constantly be adjusting its orbit to make sure it stays at that 150-kilometer size of, or sorry, 150-kilometer distance above the Earth, as well for communication. So, when in space, they can't be communicating with Earth uh, 24/7. At least that's not the case for all satellites. Sometimes they have to be within a certain range of what they call the ground station, which is essentially like the cell phone tower, where they would get all their data from the space station. So they have to make sure that they're flying over certain parts of the Earth at certain times of the day, so then they're able to um, directly communicate, get into contact with, or download information from the space station. So basically, there's so many, these are like the backbone of anything space related, because this talks about orbit of planets to each other. This talks about orbit of things that we put into space, and all of the above. Are there any more questions? And does that answer your question?
Oh, you can't see him, but he's nodding yes.
Oh, okay, sorry.
Yeah.
Perfect.
And guys, there's also a chat. You know, the space travel and exploration chat. Feel free to put questions in there as well.
Yes, that would be
If maybe
awesome.
you can't turn on
I'll
your
just
mic or
make sure.
anything, there's always also a chat box that you can use.
Mhm. Perfect. I have, yes, I can see the chat. Okay, perfect. So then let's talk about some of the other components of the orbit. So these are the components of the orbit in relation to the two bodies and how they interact with each other. When I say two bodies, I mean like the sun, you see at the center here, and then let's say this is the Earth. So that these equations talk about the relation between those bodies. So the sun, Earth, and any other two, spacecraft, Earth, and so on. But this, orbital components, are just for the individual spacecraft itself. So, um, no, they're actually, well, it's kind of how the spacecraft specifically goes around the other body. So these are just more in detail uh, ways to look at orbits than these slides. So with um, this is a very complex image to look at, and to this day, I have sometimes trouble looking at it because it's very hard to conceptualize. But basically, um, in this graph, it's as if there's some kind of body in the center here. So let's say this is Earth. And then celestial body. So again, remember that's anything outside of the 100-kilometer range. So let's say this is the International Space Station. Then all of these parameters are things that they need to consider to be able to predict the motion of, the launch of, and all of that for the spacecraft. So this is the orbit here, as you can see. The reason why it's on an angle is just so you can see some of these other parameters easier. For example, the inclination. So for example, if the inclination angle was 0, oopsie, inclination angle was 0, then the orbit would be on this plane of reference. And then of course you have all these other fancy angles with all these fancy symbols that you can specifically calculate where your celestial body, which is anything outside of space, can see. So I think we're getting close to the end, if I believe, but I can show you guys my actual rocket launch. That's me.
Like 6 meters per second thing again as it increases.
Now about the planning, the actual work.
Have any aircraft inside this area when we are launching?
All stations, this is range control. Countdown runs from T-1 hour. Check item 2. Pad supervisor, how do you read?
Range control, we loud and clear.
TM readout.
Loud and clear.
Items 7, 8, 9, and 10 are completed. Launch pad is cleared.
This is satellite manager, the payload is on.
This is now TM. TM check complete.
Check, go, no go lights complete.
8, 7, 6, 5, 4, 3,
Push.
2,
Hold.
1, fire. 1,
Yeah.
2,
You can.
3, 5.
And then approach it with a push.
Yeah, so that was my rocket launch. That is the end of my presentation. I wanted to leave a little bit of time for questions and for chatting and anything else you guys want to talk about.
That was fantastic. Thank you so much for that awesome presentation. I don't know about everyone else, but I really enjoyed it, and I think so did everyone else. Yeah. So yeah, everyone make sure to thank Miss Megan for her time today. And if we have any questions, please do, leave some. I think I'll start us off because I have a couple questions. So the first one being, so how long was the burn time on the rocket?
The burn time, I think it was pretty short. Like I think it was, oh, that's a good question. You know your stuff. And you asked me about solid versus liquid rocket too. You know your rocket science. Um, I feel like it was something very short, like 14 seconds or something.
I feel
Like
it, like it was going really fast. That's why the acceleration was really fast. So I don't think,
yeah.
but that's still. So do you know how fast it went in terms of speed?
How fast? I'm not sure, actually. I don't quite remember because we all had different roles. So my role specifically, um, I had put a light sensor on the inside of the rocket, and this is actually a big no-no for rockets because it's actually called a parasite when you have any kind of like imperfection on the surface of the rocket. But we drilled a hole in the rocket and put a light sensor facing upwards, so then we would actually be able to see like the rotational velocity, for example. So I think at one point we got to like 17 rotations per second or something like that. Like we got to a ridiculously high angular velocity, but I can't quite remember the actual velocity.
Right, 17. That's really high though. 17.
hmm
Yeah.
If I remember correctly, I hope I remember correctly.
The light sensor was sort of to measure the speed, so you drilled a hole in the nose cone, I'm guessing, and installed it up there.
I think we actually drilled it in the body of it, and basically, yeah. What I did was, since the rocket was spinning, the rocket would be facing the sun and be seeing more light every time it went around that rotation. And so then I basically looked at the time between each of those spikes in the light for the light sensor. And every time there was a spike in the light, I knew that it had gone around one more time because it can't be getting light from the ground, for example. That's not going to be enough light to actually have some kind of reading on the sensor. And so I just counted all the different rotations between the sensor, yeah, between the different peaks on the graph that we got back in our data, and yeah, and then I was able to calculate the rotational acceleration.
Wow. So you mean to say the rocket was like quite literally spinning in the air?
Yeah, that's kind of they actually want rockets to do that when they're flying because it helps keep them stable, I believe. Like it,
Right.
they kind of like every single rocket has like the slightest little like curve in its tail because you want to be able to control that kind of spin. Because if it were to spin um, for reasons, for example, like the wind, and since literally every surface has some kind of friction, no matter how smooth you make it, there's always going to be some kind of friction. You know, the wind could catch it and spin it in a different direction. And then the spin could actually then contribute to drag, which then could contribute to velocity. So basically, they try to make the rocket spin, but they do it in a way where they have control over it. So then it doesn't affect, they can account for it in all of their other parameters, for example, like in the fuel and the launch angle and things like that.
Right. So by spinning, you mean like rolling, right? Like for example, if it's like this, it was like rolling like that.
Yeah, exactly. So yeah, like spinning in the air like that.
For a second, I thought you meant like this, and I'm like, I don't know why.
Oh no. Oh, that would be interesting. That would be cool to see. However, you also hope you don't ever see that.
Yeah, exactly. That's why I was confused when you said you hope to see that. I'm like, well, I don't think you'd want to see a tumbling fall from the sky. Yeah.
Yeah.
Uh, so do we have any other questions?
I have two more questions. So my first question is in the launch video, they started like counting down, and then after the launch started, they counted up.
Hmm.
And why is that?
So that's actually a really good question. So they warned us about this before the launch that because this rocket is, it was a solid rocket, so the fuel was solid. So generally with solid rockets, it takes longer to light because the fuel is much more compacted together than it was if it were a liquid. And so when after they light the rocket, so the initial countdown when it reaches 0, that's when they light the rocket. So when the sparks go off to ignite it. And then the countdown that continued after was until the rocket actually fired. So they told us that the rocket would take 3 to 7 seconds typically to actually get off of the launch pad. And so for us, it took the shortest amount of time, the 3 seconds. So that is what that delay was just the delay between the ignition versus it getting off the launch pad.
Oh, okay. And then my second question is there was like a white structure next to the launch pad, and what was that?
Let me see. I'll go back in the video and I'll see if I can tell you. Uh, next to the launch pad.
It was yeah, that one that
This
like
one?
um
Uh,
yeah, or there was
this.
like a thing that like rotated kind of.
Oh, I know what you're talking about. That was our satellite dish. So we actually had two different satellite dishes. I'll see if I can, if you're actually able to see it in which shot. Let's see.
Fire. One,
Yeah.
two,
You can.
I think it's right after. Oh,
Yes.
this one.
Yeah.
Yeah. So that is was one of our yeah, that was one of our satellite dishes that we were using to track the data from the rocket. So it's interesting because we had one satellite dish that was automatically um, like following the trajectory of the rocket based off of the rocket simulation software. And then we had another one where students were actually sitting in the building that is right here. They were actually sitting in this building and they manually tracked the rocket just to see the comparison of the data. And they manually tracked it based off of some of their predictions, based off of the simulation software and it was kind of like an active way to participate in it. But yeah, they needed to directly point the satellite to, or the satellite dish to it to be able to get a better transfer of data.
Okay. Yeah, that's very cool.
Yeah, that is. It also rotated extremely fast. Yeah, that was really cool. But it is 2:21, so everyone in this session, you do have your second Innovate Alley workshop that you should be getting to. And I believe some more people will be joining us for the second session of this current workshop. So thank you all for attending. Thank you all. I hope you all had a great time over here. And yeah, I guess everyone should be getting to their, their next workshop where they're supposed to be.
Okay, bye.
Bye. It was nice meeting you all.
Yeah.
You as well.
Thank you.